Hey guys, welcome to our YouTube channel. So today we are going to see about pi by 4 DQPSK or the p by 4 DQPSK. The pi by 4 shifted QPSK modulation is a QPSK technique that offers a compromise between no QPSK and QPSK in terms of allowed maximum phase transitions. The signaling points of the modulated signal are selected from two QPSK constellations which are shifted by pi by 4 with respect to each other. So in other words, it's just a compromise of QPSK 90 and OQPSK minus 90. Sorry, QPSK 90 and OQPSK 90 degree. So pi by 4 is like it makes it to plus or minus 45 degree or plus or minus 135 degree. It is a non-coherent one, so no need information from the receiver side. It can be used in multi-path feeding. Bits are always 180 degree. So this is what the constellation diagram 2 tells you, that any angle you take up, it results in 180 degree. So this is what I was telling you about. See, this is 45 degree, this is 135, minus 135, minus 45 degree. This is what you get your phase shift values. So what does a transmitter model do? Pi by 4 QPSK transmitter model. So I'll tell you what. The input data is partitioned into two parallel data streams and is passed into the low pass filter, a multiplier, and then added, which is given to the amplifier, which gives the output as pi by 4 QPSK signal. Okay, this is when differentiated, you get the formula as. So this is the formula you're getting it. Okay, so your I of k is the amplitude. Okay, and m of k is the input in phase and quadrature, which is this one. Okay, so the signal mapping makes it combined with the input and the I of k. Okay, so I of k is the cos decided from the previous state in phase and sign. Okay, and q of k is also the same, which is the previous elements of I of k. And LPF modulates each signal. When I of k is expanded, you will get your pulse shaping function and symbol period. Okay, so the final signal will be like cos omega ct. Okay, your in phase quadrature gets multiplied with cos, and the quadrature gets multiplied with sine. So this is what cos with in phase and sine with quadrature. Okay, so differential detection of pi by 4 technique. Okay, um, so this can be in other terms like baseband differential detection. Okay, so what happens here is omega k is equal to cos phi of k minus del. I'll show you. So this is the formula, and del is the phase shift due to noise, propagation, etc. Omega k and z of k passes through differential decoder based on x of k is equal to omega k minus 1, z of k minus 1, and y of k becomes like z of k into omega k minus 1 minus of omega k into z of k minus 1. So, okay, so what is x of k and y of k? They are the differential encoders. So del is a phase shift due to propagation. Okay, um, and the phase shift occurs due to propagation. Okay, um, differential encoding happens by a rule. So you have a decision devices. Okay, so decision devices checks whether 1 or 2 is transmitted, and the multiplexer combines and you get your original signal. If your SI is equal to 1, then SK should be greater than 0. If your SI is equal to 0, then your SK should be lesser than 0. So that's a condition here, and omega of k and z of k are your tuned frequencies. Okay, and cos and sine are generated by local oscillators. Okay, so this is your IF detection, elimination of local oscillation. Why we eliminate is for time delay. Okay, and the elimination purpose helps us by cost and design. Cost gets reduced and design becomes simple. Okay, so in detail, uh, the BPF is designed to match the transmitted pulse shape so that the noise power is minimized. The bandwidth would be like 0.57 by TS, which is a symbol period. Received signal is differentially decoded by delay sign and two mixers. In delay line, every symbol is delayed by one symbol duration. The decision device is decided as follows: Si is equal to 1, your x of k should be greater than 0, or Sq is equal to 1, your y of k should be greater than 0. Okay, so that is the same decision devices which I told you is to check 1 or 2, and yeah, um, and LPF is for modulating each signal. Okay, and you get your demodulated output. Now, FM discriminator, this is the third technique. So this is like the input signal is filtered using BPF, uh, and then hard limited using limiter circuit to remove the fluctuations. Okay, so FM discriminator extracts the instantaneous frequency deviation of the received signal. The demodulated signal is then fed into integrate and dump circuit and gives the phase difference between two sampling instants. The phase difference is then detected by a 4-level threshold detector to obtain the original signal. Okay, so it's like limiter removes any envelope fluctuations. FM discriminator extracts the frequency deviation of RXX signal. So 4 level, it's like 4-level threshold detector is like detects the signal based on the phase difference. Integrate and dump extracts the phase difference. Parallel to serial acts as a multiplier over here, and there you get your demodulated output. So this is the power spectral density comparing to. Okay, and here ends the video. Thank you.